Welcome, everyone. In the world of business, almost every major decision, from how much to produce to what price to set, it really all boils down to understanding relationships. And the simplest, but also the most powerful tool we have for understanding those relationships is the linear function. So today, we're not just going to learn some math, we are going to master the tool that is truly the foundation of cost analysis, revenue forecasting, and strategic planning. I want you to see this not just as a formula, but as a way of thinking that you're going to use for your entire career. So here's our roadmap for today. We'll start by defining what a linear function actually is. Then we're going to decode its equation, really digging into what each part means in a business context. From there, we'll roll up our sleeves and build a predictive model using some real-world data. And then the crucial next step, right? We'll use that model to make a tough managerial decision. And to wrap it all up, we will cover some of the most common errors that can completely derail a forecast so you know exactly what to watch out for. Okay, let's start right at the foundation. The subtitle here really says it all, the straight line of business. Now, why a straight line? Think about it. In business, what do we crave more than almost anything? Predictability. And a straight line means a consistent, predictable relationship between two things, like, say, cost and production. So before we can really leverage this amazing tool, we need to understand exactly what it represents and why that consistency is so incredibly valuable. So at its absolute core, a linear function models a relationship of perfect consistency. A really good way to think of it is as a for every relationship. For every 1 unit we increase our input, let's call it X, maybe it's one more product we make, our output, Y, say our total cost, changes by a constant, predictable amount. This straight line predictability is, believe me, a manager's best friend. For every extra widget you make, your material cost goes up by a set amount. For every additional sales call, your revenue might increase by a set amount. It's this beautiful consistency that lets us turn data from the past into powerful insights about the future. And this is the language we use to describe that powerful straight line, f of x equals mx plus b. This is what we call the slope-intercept form, and I promise you it's about to become your new best friend. Now, it looks simple, but don't let that fool you, because within these simple components, M, X, and B, lies the entire story of a business operation. You've got the dynamic costs that change with activity, and you've got the static costs that form your foundation. So let's break down that story, piece by piece.
All right, so let's decode this equation's DNA. To truly master this formula, you have to understand what M and B actually represent in the real world. I need you to see these not as just letters in a math problem. They are concrete, tangible business concepts that every single manager has to understand to know the financial health of their operation.
Okay, let's start with M, the slope. M represents the dynamic part of your business. It's the engine of change. It tells you the precise rate at which your total cost or revenue changes for every single 1 unit increase in activity. In a cost model, M is your variable cost per unit. That's the cost of raw materials and direct labor for making just one more product. In a revenue model, M is simply the price per item you sell. It's the marginal change. And understanding M means you understand the core operational drivers of your entire business. So, if M is the engine, then B is the foundation. It's your starting point. The y-intercept represents your fixed reality. These are the costs you have to pay even if you produce absolutely nothing. Think of B as the cost of just opening the doors on day one, your monthly rent, your insurance premiums, the salaries of your administrative staff. It's a constant. It's a fixed cost that doesn't change with production volume. A manager who doesn't have a firm grasp on their fixed costs, on their B, is, to put it bluntly, flying blind. Now, as you do your work, you're going to run into two main forms of this equation. The one on the right, the point-slope form, think of that as your workshop. It's what you use when you've got raw data points, like production numbers from last month, and you need to build the model from scratch. The one on the left, the slope-intercept form, that's your showroom. It's the final, clean, easy-to-read model that you present to your boss and use for forecasting. So we typically start with the logic of the point-slope form to find our variables, and then we express our final answer in that elegant slope-intercept form. All right, theory is great, but the real learning happens by doing. So let's step out of the classroom for a minute and into the manager's office. We are going to take two simple pieces of operational data, and we are going to forge them into a powerful predictive tool that can guide financial planning for an entire quarter. Okay, so imagine you're the operations manager of a small manufacturing firm. You're looking at your reports from the last 2 production runs. In the first one, you made 100 units, and your total cost was $3,000. In the second run, you scaled up production to 200 units, and the total cost was $5,000. Now, this is all the information we need. It's incredible, right? With just these 2 points in time, we can build a linear model to forecast our costs at any production level we can imagine. We're going to follow a very precise 4-step methodology. This isn't guesswork. It's a repeatable system that you can use over and over. First, we'll calculate the slope, m, to figure out our variable cost per unit. Second, using that slope and one of our data points, we'll solve for the y-intercept, b, to uncover our fixed costs. Third, we'll put these pieces together into our final powerful equation. And fourth, and this is a step that so many people skip, but it is absolutely crucial, we're going to test the model to make sure it's accurate. Okay, step 1, let's calculate the slope. The formula is the change in y divided by the change in x. Let's translate that into business terms. It's the change in total cost divided by the change in units produced. So, our cost went up by $2,000 when our production went up by 100 units. The math is simple, right? $2,000 divided by 100 gives us a slope, an m of 20. And here's where it gets really interesting. What does this $20 represent? This is our variable cost. For every single additional unit we decide to produce, our total costs are going to go up by exactly $20. We've just uncovered a core financial metric of our entire business. Now for step 2, finding our fixed costs. We just take our standard equation, y equals mx plus b, and we plug in what we already know. So let's use our first data point. We know our total cost, y, is $3,000 when x is 100 units, and we just figured out that m is $20. So the equation becomes $3,000 equals $20 times 100 plus b. Well, the variable cost portion is $2,000. So if the total cost is $3,000 and the variable part of that is $2,000, what's left? The remaining $1,000 has to be our fixed cost, our b. And just like that, step 3 is done. We now have our predictive model. Total cost equals $20 times the number of units plus a fixed cost of $1,000. We've literally turned 2 data points into a forecasting machine. Okay, so this is the crucial point. We have not just completed a math problem, what we've actually done is create a business intelligence tool. The numbers on a page are totally meaningless until we use them to make a smarter decision, to allocate our resources more effectively, and to plan for the future with real confidence. And here it comes, the moment of truth. The CEO walks into your office. Hey, we just got a huge new order. We need to produce 500 units next month. I need a cost forecast for the big budget meeting this afternoon. What's the number? See, this is no longer a theoretical exercise in a classroom. How do we use this powerful equation we just built to answer this absolutely critical question? And this just brilliantly illustrates the power of what we've done. The answer is now simple, and more importantly, it's defensible. We plug 500 into our model for X, so the variable cost will be $20 times 500 units, which is $10,000. Then we add in our fixed costs of $1,000. The total forecasted cost is $11,000. You can now walk into that budget meeting with confidence and say, to produce 500 units, we need to budget $11,000. You've just transformed raw data into actionable intelligence. Now, before we finish, I want to address something absolutely critical. In business mathematics, unlike a classroom exam, a small calculation error doesn't just lower your grade. It can cascade into a massive strategic and financial mistake. So let's look at the single most common pitfall I see when people build these models, one that can lead to truly disastrous decisions if you're not careful. A frequent and, frankly, disastrous error is inconsistency when you're calculating the slope. You have to maintain the same order for your y and x values. Notice the correct formula on the left. It's 0.2 minus 0.1 in the numerator and 0.2 minus 0.1 in the denominator. Now look at the mistake on the right. The student has accidentally flipped the order of the x values. This will give you a negative number in the denominator, which results in a negative slope. Can you imagine? Your model would predict that your costs actually go down as you produce more. Imagine trying to make a budget based on that assumption. It would be catastrophic. I really want this to stick with you. The key takeaway here is that precision, attention to detail, and double-checking your work, these are not just academic exercises to get a good grade. In your career, they are markers of professionalism. They are fundamental to sound financial planning and responsible decision-making. The numbers simply must be right. And so, I'll leave you with this final critical thought. We've seen the power of a linear model today, no doubt. But its greatest strength, its beautiful simplicity, is also its greatest weakness. Our model assumes the variable cost per unit will never change. But what happens in the real world when you try to scale up to, say, 10,000 units? Do you start getting bulk discounts on your materials, causing your variable cost to actually decrease? Or do you have to start paying workers overtime and straining your machinery, causing it to increase? So the most important question a manager can ask is this: at what point does my simple, straight-line model become a dangerous oversimplification of a much more complex business reality? Thank you.